Hello guys, so today we're doing LeetCode question 230, Kth smallest element in a binary search tree. Question is, given the root of a binary search tree and an integer k, return the kth smallest value, one indexed of all the values of the nodes in the tree. So example 1, this is a root of 3 with a left hand node of 1, right hand node of 4, 1 has a right hand node of 2. The k is 1, so you have to find the smallest element, the output is 1 is the smallest element. Now the tree here is 5, left hand node of 3, right hand node of 6. 3 is left hand node of 2, right hand node of 4. 2 is left hand node of 1. So the k is 3, we have to find the third smallest element, and the element is 3. So a binary search tree, the left subtree always has to be smaller than the node, then the root node, and the right subtree has to be smaller than the root node. So for example, if we go here with, let's use the current one as an example. So it was 3. Let's go back. 3, 1. See, the left side is smaller than the node, and the right side is going to be bigger because it was 4. And again, the right side should be bigger, so this is 2, but it's still smaller than the left side here. It's still smaller than 3, which is the main root. So the way we do this is we have a counter to count smallest values up until we get to k. So we start at 0, then we do a depth of search because we know that the left side has to be smallest. So we go straight from the left. We count as soon as we go as far as possible to the left. We increment the count by 1, and when it is k, we return the root value. So now we're at 3. We check to the left, know the left. Okay, let's say we have to return the first. Can the node go any further left? No. So now we return 0, go up. Now can't go any further left, so we increment the count. Count is now 1. K is also 1 in the situation. 1. K is 1. So I'm using my left hand. So now that k is equal to count, we return count, which is 1. So 1 is the smallest element in the tree. And let's use the other one as an example. So let's use 5, 3. 5, 3, okay, oh, sorry. Let's rub this out. I think k was 3. So the tree was 5, 3, 4, I believe. So 5, 3, was it 5, 3, 6, 4. Okay, 5, 3, 6, 4. Let's do this. 1, 2. Change it up a bit. So I'll show you what happens instead of going left, 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 left. So k is 3. We have to find the third smallest element. So again, we increment a count at 0. So we start from 5. We go left. Can we go left again? Yes, we can go left. Can we go left again? No, we can't. So we increment the count by 1. Count is now 1. Is count equal to k? No, k is 3. So we can't go left anymore, so we go right. Okay, can we go left? No. Can we go? Okay, so now we're at 2. We increment the count by 1. Is count equal to k? No. So we go right. We go up by 1. And we go up by 1 again. Now we complete the left subtree, so now we're at the third node. 3. We increment count. Now we're at 3. Is count equal to k? Yes. So we return the node at k. The node that we're at now, which is 3. And that is the first smallest element. Now let me show it on its code. It's done in code. Okay, so first we increment the count, which equals 0. Ooh, count equals 0. Then we just have to increment the result. So if the tree is empty or k is 0, we return the result, which is 0. And otherwise, we set the result as the node when we find k. So then we create depth of search, so function DFS pass the root. Then if no root, we return null. Else we do depth of search root dot left. Then we do count plus plus. Oh, And if we check if k or count is equal to k, then we set result as root.val and we return. So this sets the result as a value once you found the kth element. Then do the same for root.right, root.right. Okay, and then we execute the function. So we pass in the root and we return result. Okay, let's run. See that passes, let's submit. As you can see, this is one of the fastest methods. This is time complexity of O(n), as we're looping through the whole tree. Worst case. Thanks for watching.